Great pleasure to have Summer here to speak with us. She's one of our own. That she came to BYU the same year as me, and she was brand new, a newly minted PhD, and she's just done amazing things here at BYU. And she's going to talk to us a little bit about climate and ice, But Summer did her undergraduate work here at BYU and then went to the University of Washington and worked with some of the best people in the world on geology and Earth systems. What's really unique in the sciences is that she was hired straight out of her PhD without a postdoc, came here, got thrown into teaching and expectations related to research, and it's just done remarkable work with consistent funding from the National Science Foundation. Received both the Department of Geology and the college awards for research. And she was just telling me about. She was a fellow of the National Academy of Sciences, their Frontiers of Science. That it was a program where they handpick 100 of the most promising young scientists from around the U.S. across all disciplines to come back and meet at the National Academy and to exchange ideas and sort of really lay out the framework and have a vision for what science is going to be like for the next 30 years. And so Summer was one of the individuals invited to come to that and to speak at it and to speak about what she's going to tell us about today. And so with that, Summer.
All right, well, I'm very excited to be here, actually, and the first thing I need to do is figure out if I know how to work this. So they have my presentation back there, but there we go. All right, we'll see if we can go back to the first slide. So today I'm going to focus a lot, fairly broadly, on cryosphere climate interactions, and a big piece of this at the start will at least be to define what do we mean by the cryosphere. Hopefully cryo is at least a little bit of a hint at that. But in general, when we study the cryosphere, we are talking about the ice in the environment in all of its forms, okay? This is also just an opportunity to be able to show some pretty pictures, so we'll go with that. So the basic outline here is going to be defining what the cryosphere is, and from there talking about why we should care. Who cares about the cryosphere, and in particular, what role it plays in the climate sciences, our understanding of climate change, evidence of climate change, and in particular, impacts on climate itself, as well as on society. And then if there's time, I'll show some examples from some of our work in the Himalayas. All right, so when we think about the cryosphere, first of all, and we think about Earth systems, right? We usually think of 4 systems, right? The biosphere, especially when we're talking about the Earth's surface, okay? Biosphere, atmosphere, lithosphere, and hydrosphere. Cryosphere tends to be the forgotten brother of the earth sciences, okay, and it gets wrapped up into other things quite a bit. So we'll talk a little bit more about exactly what that is today. So this is a map. It's a little bit of a funky map, right? So North Pole's in the center, and then we're headed this direction towards South America here, and then this direction towards Australia there, and Antarctica towards the left side of this map. And this is showing the different components of the cryosphere. The cryosphere includes snow, and that means formation of snow and ice in the atmosphere itself, deposition of snow on the surface, and all of those processes. Sea ice, ice shelves, ice sheets, glaciers and ice caps, permafrost in all its various forms. So it actually crosses a really wide range, all right? And this map is showing the approximate maximum distribution of these, all right? Some of these you know well. Snowpack, highly heterogeneous in space and time, right? So this outline here into the US, right, this shifts from season to season. So this is just showing roughly maximum extents. All right, so when we talk about snowpack, we're talking about what we're familiar with, maybe not this winter, but in a typical Utah winter, lots of snow, right? We're also talking about just snowflakes in general. I don't know if you can see this hexagonal crystal right here. This is a photo I took in a snow cave in Antarctica. And this single ice crystal right here is larger than a tennis ball. Okay, so these come in many shapes, sizes, and forms. And snowpack covers a very large area. So if we come back here, much of the northern latitudes affected by snowpack, as well as high elevation regions, of course. Okay, more snowpack in the northern hemisphere because it's more continental landmass for snow to end up on. Sea ice, by comparison, also has a fairly wide distribution. These white areas here, also very seasonal, but this isn't from the atmosphere. This is ocean water frozen in place, okay? And it also takes many different forms. So this is an image of sea ice in the Arctic. It's really thin in this area, really broken up. It's sort of at the tail end of its life in this case. This is an image I took, again, in Antarctica along the coast of sea ice, and it's an incredible jumbled up dynamic mass, and you can hear it. It's just crunching and grinding, and it's incredibly loud and dynamic. Okay, it's not a simple, easy, stable system. All right, and it spreads throughout from this jumbled mass to very sparse area. Okay, so that's sea ice. The next one I'm going to jump to is actually ice sheets. Today's world, we have two ice sheets, right? We have the Antarctica ice sheet and the Greenland ice sheet. Technically, this is actually two ice sheets, but we won't go into that. And these things are large, okay? These are not small bodies of ice. So this is the Greenland ice sheet up here, and it's about the size of Alaska. Antarctica, by comparison, is the size of the continental US and Europe combined, and that's just area. If you take it by volume, this thing is huge, more than a mile deep on average, all right? This is a lot of ice trapped in our polar regions. In fact, these two ice sheets make up the vast majority of the fresh water on Earth, by a lot, okay? And so most of our world's ice is actually tied up in regions we can't actually get to very easily. But they have a big impact on climate and in particular on sea level rise, all right? Something we'll talk about here in a little while. And they also take on different forms. So if you're standing in the middle of Antarctica, this is where some students and I were working, and you look around you 360 degrees, this is what it looks like. It's just an ocean of snow and ice, okay? That's it. And on occasion, you even see waves of snow, right? So it really does on occasion look like an ocean as the wind blows it around and forms sort of cool little features. Greenland's a little bit different. So Antarctica, very, very little melt. It's below freezing all year round for most of the continent. The only ice loss is the calving of big icebergs around the edge of the coast, whereas Greenland, and here's some people for scale, you form massive meltwater rivers that flow and they actually carve into the ice sheet. I wouldn't recommend rafting this river. This particular stream right here plummets more than a kilometer straight to the base of the ice sheet itself through a hole, okay, or a moulin. And this is actually important because changes in meltwater influence how much meltwater gets to the base of the ice sheet, right? And wet ice is slippery. I think we can all agree on that, right? So if you change the amount of water at the bed of an ice sheet, you will change how much it moves, how much it flows, and how it changes over time. All right, so both of these ice sheets, they're quite a bit different from each other. In fact, each one is extremely unique, both with potential players in climate. The other thing to realize about ice sheets and glaciers, they're not just big blocks of ice sitting there that slide at the bed. Okay, that's not the only way they move. They're actually a whole lot like silly putty. So if you take a blob of silly putty, ball it up and set it here, it'll start to flow under its own weight, under the force of gravity. Ice or glaciers and ice sheets, by definition, flow under their own weight, under gravity. So they're actually deforming over time and flowing. So even if they didn't slide at the bed, they would still be moving, carving out the landscape, and affecting the world around us. All right, so those are the ice sheets. The edges of the ice sheets, especially in regions like Antarctica and parts of Greenland, the ice sheet flows all the way to the coast. Now, when it hits the coast, it forms what we call ice shelves. So if I can get this to advance, here's a picture in Antarctica again, standing on the ice sheet over here, and you can see the ice flow from off the continent and onto the ocean. Now, this is different from sea ice. All right, this started on the continent, flowed potentially a very, very long way, and is now floating out on the water. But we know what happens to ice when it interacts with water, right? It starts to chew it up, it cracks, it breaks. This looks nice and flat, but if you look at the edge of it, these ice shelves can be 1,000 meters or 1,000 feet in thickness or more. Okay, these are massive. This is where icebergs come from. This is where you get the calving off of the ice shelves that gum up shipping channels, sink the Titanic, all those sorts of things, okay? But this is how ice from Antarctica and largely from Greenland ends up in the ocean, okay, and affecting sea level and ocean circulation in various ways. All right, so the next one, my personal favorite, okay, are mountain glaciers. And this is an image of Everest looking from space, okay? So this is actually from the space station itself, so pretty amazing image. Everest here, and you can see the glaciers flowing out here. Unlike ice sheets, these are kind of trapped in their topography, and then they create their own topography. So Everest is there in the shape it is because these glaciers are eroding back into it with the ultimate goal of just taking Everest completely off, right? And that's what glaciers do. They actually limit how high topography can get. Because as topography gets higher, you get more and more ice, and the ice carves it back down. Topography has a hard time getting much above that, all right? If we go on the ground here and look at what these glaciers look like if you're hiking into this region, so this is actually a region in Bhutan, we'll talk about it later, and you can see this ice nestled up in here. This particular one right here, this is the toe of the glacier, and it's 1,000 feet thick, okay, at the toe. These are not small glaciers. In general, scale can be really hard. So we see these glaciers, and they can be down in here. I don't know if you can see this, but this is just lush with vegetation. This is a really wet area, trees, bushes, okay, good grazing ground. One of the areas we're working in is a nice comparison to that. So this one, by comparison, is extremely dry, high, and cold. This is a region we're working on also in Bhutan. Scale here is really hard. I don't know if you can see it, but my tent, it's a bright orange 3-man mountain hardware tent. It's in this image, okay? This will give you a sense of scale here. So here's the ice up in here. Here's kind of a grayish rubbly moraine. There's a darker moraine right there. We're going to zoom into this area. There's my tent right there on that moraine. Okay, so if we back out, this single glacier is massive. Okay, these are not small bodies of ice, right? All right, so going on, the final component is permafrost. This is probably the one people are less familiar with, but this is just water frozen in the ground. So water seeps into the ground, we get groundwater, gets cold enough, it freezes, okay? And it's actually quite extensive. We see it across high latitudes, but also in mountainous regions, okay? It has a big effect. And it's obviously oftentimes more difficult to see, but it has its own footprint on the ground. So on occasion, it does show itself, and it creates really funky features on the surface as well. So these stone circles are nature sorting itself, okay, in the permafrost regions. So ice occurs in many, many different forms, and if we look back at here, it actually affects every single continent on Earth with one exception. Australia is the only one left out of this, okay? Africa has snow-capped peaks. It also has glaciers, okay? So even Africa's got some snow and ice on it. So most of the world potentially impacted by the cryosphere. So let's talk a little bit about what some of those impacts might be, all right? So first is, cryosphere is one of the really, really clear examples of climate change itself, right? If you warm up the atmosphere, ice melts. This is pretty intuitive, okay? Most elementary school kids can understand that one, which makes it a really good thing to look at, okay? If you look at changes in the cryosphere, you're seeing changes in climate. And we are seeing changes. We're seeing changes in our mountain glaciers, snowpack, sea ice sheets, permafrost. All of these different components are changing. And I'm just going to show you an example of a couple of them. So let's start with sea ice, okay? This is a graph showing changes in sea ice over time and projected into the future, okay? So the black line is the observed. Dotted is historical reconstructions. So given all the data that we have, reconstructing sea ice extent in September. So this is at the end of the summertime. It's at its minimum extent. And then we head into winter and it starts to grow again, all right? And what we can see here is from the early 1900s through to present day, a steepening decline in sea ice extent in this region, with projections being extremely varied depending on both uncertainties in the model and which scenario we choose, right? And so William actually talked a lot about this last week, but depending on we continue at business as usual, or we absolutely just stop emitting greenhouse gases, or we allow it to ramp up with population growth, right? Will affect how much this changes, anywhere from leveling off eventually to having fairly steady, but about half the sea ice we had at the start of the 1900s, to no sea ice at all by the end of summers, depending on the scenario. And we'll talk about why that might be important, okay? All right, another one, again, my favorite, glaciers. They used to be the poster child for climate change, right? You saw them everywhere. Now it's the polar bear, but you still see glacier pictures on occasion. So here's images from Peru. This is a Peruvian glacier, July 1978, July 2004. Big changes in ice, right? A little bit closer home, this is the Cascades. This is South Cascade Glacier, 1928, 1959, 79, 2010, right? And we can keep doing this. We can hop around the world. If we come really close to home, this is a group of BYU faculty in wool suits in 1908, August of 1908, on Timpanogos. And this is a massive crevasse, okay? And that crevasse forms because of flowing ice. You form nice big cracks in it. This was a true glacier in 1908. And in fact, in July 30th of 1949, this is a ski race happening in that same region. It's still a glacier. Okay, now 2003, exact same area. What we see now from about the 1980s through present day is just waxing and waning of snowpack on Timpanogos. We lost this glacier somewhere around the 1960s. Okay, so closer to home, we still see this impact. Now, these glaciers, again, we have glaciers on every continent except Australia. This means that we can go and we can look at what's happening around the world. And if we actually do that, potentially, okay, this is a map showing various glaciers, different locations, both hemispheres. These are just examples across the region. Alps, Switzerland, those regions, historical records go very, very, very far back. They've kept really good records of glacier changes. Almost everywhere else in the world, our observational records are really short. Okay, we just haven't been tracking them as well. But you can see that you get a lot of variability, right? Some have on average retreat, but you had a period of advance. Okay, we kind of expect that. Here's the Franz Josef Glacier in New Zealand. Really, really rapid retreat and a little bit of recovery here, but then in the last 20 years, it's actually tanked even more. Okay, so a lot of variability in that, which we expect. But if we average all those records together and get the average change in length over the entire world, what we see, and again, we exclude the Alps because they sort of dominate the records. We want to see how much they're biasing things. But what we can see is around 1850, mid-1800s, rapid decline on average of glaciers around the world on every single continent. Okay, that doesn't mean every glacier is retreating, but on average, actually about 95% of them are. All right, so massive change. All right, so the cryosphere has played actually a central role as evidence of climate change, in part because they aren't thermometers, right? This is a natural system responding to changes in climate, and you can see it. It's easy to see, and it's relatively easy to measure. But they also provide records of climate change itself. Okay, so another comparison to the instrumental record, right? What has climate actually been doing over time? And in particular, extending potentially the observational record much further back than we could otherwise do. An example of that are ice cores. Okay, this is where we go into ice sheets, some high alpine glaciers, and literally drill a hole and pull up plugs of ice, right? Ice at the surface is the youngest, gets older as we go down, and we can pull that archive out and look at what's been happening over time. So this is one of the longest ice core records. This is an Epica ice core from Antarctica, all right? And this record goes back 700,000 years, right? At very high resolution, actually. This proxy, this black line here, is a proxy for temperature, okay? So peaks are warm periods, lows are cold. We're seeing interglacial, glacial cycles, right? So interglacial, glacial, interglacial, glacial, on and on. Last glacial conditions, right? When we had massive ice sheets covering much of northern North America and Fenno Scandinavia, and then into the present interglacial period. But what's nice about ice cores, at the same time we can get a proxy for changes in temperature, we can see what greenhouse gases we're doing because the ice traps little bubbles of the atmosphere. So we can look at what the atmospheric composition was at the same time that temperature is changing, or roughly the same time. So the blue curve here is showing what CO2 has done in the past, right? So we can see how it marches in lockstep with temperature. Same thing with methane. Does anybody know where we are today in CO2 levels? Almost 400, right? So somewhere up in here compared to what nature has done on its own over the last almost 1 million years, right? What about methane? Quite a bit scarier, right? It's actually a little bit closer to the top of this slide, right? So we can see what nature has done on its own and look at how climate has changed in combination with that. Now, we know the pacing of these glacial interglacial cycles is largely driven by the periodic changes of Earth's orbit around the sun. Okay, so at times our orbit is such that we kind of tend towards cooler conditions. And we know what that is, right? That's known really well, and we know what the changes in radiation are. You can't explain even 1/3 of the temperature changes seen with that orbit alone. There's no way to do it. We would not have the massive ice sheets. We wouldn't have the big sea level changes. The only reason the temperature changes are as large as they are because of these greenhouse gas changes. They are a significant part of that change in climate over that period of time, okay? But what this lets us do is begin to quantify how sensitive Earth's climate is to changes in greenhouse gases, and it provides a target for climate models, right? So climate models don't just try to model present day or future. One of their really good targets are in the past to see whether they can reconstruct climate for these changes in greenhouse gases. Do they get back what the glacial conditions were like? So these ice core records provide us a long timescale history of what nature does on its own, and it isn't just some stable flat line, right? It does vary, but we can use that to compare recent climate change. One of the big things being not just that we've exceeded what nature's done on its own in the past almost 1 million years, but this is a steep curve right here, right, in greenhouse gases. That transition from glacial to interglacial is actually really fast. But our rate of change in greenhouse gases today is 275 times the rate that nature's ever done on its own. So it's not just the magnitude that's important here, it's the rate. We're doing it really, really fast, okay? So we also use ice cores to kind of fill in gaps in the instrumental record. So this is some images of some of my students in Antarctica. We're actually working in this region here. It's on the West Antarctic ice sheet, all right? So there's Jessica. She's playing with an ice core. This is actually a colleague from NASA. The snow pit is the coveted position because you're shielded from the weather, right? And you have to remember, Antarctica is the highest, coldest, windiest, driest continent on Earth, right? These are really extreme conditions. And so it is a desert. But because it is so cold, the ice doesn't melt, right? So what's put down on the surface? It stays there, which gives us really nice records. In this case, again, remember how big Antarctica was? We have fewer, actually, if you compare Antarctica to just Provo, Antarctica as a continent has fewer weather stations than the city of Provo does. Okay, in part because under these conditions, they just don't last. Okay, it's really hard to maintain them, and they don't record very well. But we can fill in those gaps, again, by drilling ice cores. And this right here, this is a paper published by one of my students, but also with William Christensen and several other students. So several faculty and students have been involved in this research. And what we did is we reconstructed snowfall over the last 30 to 40 years to look at what's happening in the interior of Antarctica. And most of the projections have said that, okay, as temperatures warm, hydrologic cycle speeds up, we should actually get more snowfall into Antarctica, and this would be really good because it would help offset some of sea level rise, right? Because if it's all going just into the ocean, that's the wrong direction, right? If we can get more of it to stay in Antarctica, that would be really good. Unfortunately, our results were counter to what we wanted or expected, and what, with his magical statistics, William was able to show is that at every single location for 6 different ice cores, there's actually been a statistically significant negative trend in accumulation in this region of Antarctica, which doesn't go in the right direction, all right? So we're able to start to look at some of these regions in a lot more detail by filling in with these ice cores and starting to understand climate a little bit better in regions where we don't have the observational record. So we can go back and get it in other ways. All right, the other thing we can do is we can actually go to those mountain glaciers themselves. So if you remember this record, this image right here showing changes in glacier length, well, we can actually go in, and this is work by Johannes Erlemans. He went through and he said, okay, easy. We're going to model. Sorry, I'm going to use the model word here, William. He doesn't believe any model unless it's a statistical model, apparently. No. Apparently, I'm supposed to use another term for it. What did you call them? Glacier simulator. Okay, so no, what he did is he asked the question, how much would temperature have to change in order to explain these changes in glacier length? Really simple, really easy. Doesn't use anything from the instrumental record, doesn't use anything from remote sensing, a completely independent record of changes in temperature. This is the reconstructed temperature from glacier length that he gets out here. This is the black line is the global average, and then each of these is from a different region. On this image over here, and I'm not sure why you plot it on a different scale, but this is from the instrumental record. And what he was able to show, and this was a really important paper, because at this time, people were questioning the instrumental record, in part because these are in populated areas. So the question was, how much of this warming is due to an urban heat effect, right? So you get more cement, you get more people, you grow your population, you expect temperatures at these local locations to go up. How biased are these records? Glaciers are not where people live for obvious reasons, okay? So they're a long ways away from that urban heat effect. And what he was able to show is that he gets the same change in temperature within 0.02 degrees Celsius within the uncertainties as compared to the instrumental record. It was an independent record of changes in temperature that said, no, it's not the urban heat effect, okay? So this was a very, very important piece of our understanding of that climate system that came from the cryosphere. All right, not only are they records of climate change, but they actually impact climate change itself, all right? And they do that through three basic things. One is the albedo. Albedo is the idea, is just the reflection of solar radiation, okay? So white t-shirt reflects more sunlight. That's why we wear a white t-shirt in the summertime. Black absorbs more of it. You feel hotter if you wear a black t-shirt, right? Ice and snow tends to have a really high albedo. It tends to reflect a lot more of the solar radiation on it. The other effect it can have is topography. Now, this really only operates on very long time scales. But you can think about Antarctica, right? That's a massive plateau, and it's a big boulder in a stream. It creates waves and winds that wouldn't be there if we didn't have that topography. So over long time scales, changes in the ice sheets actually affect atmospheric circulation. All right, and we've seen that during glacial and interglacial cycles as well. And the last one is ocean circulation. So to start with, let's look at the albedo, all right? If we start here with an initial change in temperature, for whatever reason, okay, let's say we increase temperature a little bit. If we increase temperature, we melt ice. So sea ice extent decreases. But when we decrease sea ice, we have more black ocean water, all right? And that ocean absorbs more of that solar radiation, which warms up the climate more than what we started with. So we warm the temperatures more, that decreases sea ice again, temperatures warm more, and we get what's called a positive feedback, okay? And there are a lot of feedbacks in the Earth's climate system. So this graph right here shows the dominant feedbacks. There's lots of different measures of this, okay? Feedbacks are actually quite uncertain. Don't worry about the numbers right here necessarily, but anything above 0 means it's a positive feedback. It's something that tends to amplify the initial changes in climate. So you kick the system a little bit, but these things make the change much larger than it would be. Things that are negative dampen that change. And we just don't have very many negative feedbacks in the climate system, not on these time scales. Okay, on long time scales, you'd have to include weathering, but that operates on many, many, many thousands of years, okay? And it would be a strong negative feedback, actually. So water vapor, positive feedback. Warm the climate system, speed up the hydrologic cycle, more water vapor in the atmosphere. Water vapor is a very, very good greenhouse gas, so you warm up the climate system more, and you can see where that would continue. Clouds, clouds have two competing effects, but recent studies have shown that it dominantly has a positive feedback effect. Albedo is actually not one of the largest positive feedbacks, okay, in snow and ice, but it is a positive feedback. This is temperature lapse rate. So this is how quickly temperatures get cold as we go up in the atmosphere, right? And that has a negative feedback on the climate system. Water vapor and the temperature lapse rate are actually related. So when you put the two together, it's still a positive feedback. And then this is the total of it, okay? So these feedbacks are huge, actually. They're a big piece of this climate system. And this spread shows you just how uncertain they are, okay? They're a big uncertainty. So we have a pretty good understanding. If you double CO2, you're going to increase the radiative forcing by 4 watts per meter squared, if that were the only thing to happen. The problem is the Earth systems all respond, okay? And they amplify that and that amplification is what's of critical importance in many of these areas. The other thing that ice does, though, especially sea ice, is it actually impacts ocean circulation, and in a very dramatic way. So this is just a really, really simple cartoon, okay? Don't read too much into this. But this is the equator, 90 degrees south, 90 degrees north. We have no ocean here because that's Antarctica, okay? North Pole, we do have an ocean there. In the sort of towards the low latitudes, northern hemisphere, that's our biggest warm ocean source circulation here. But most of the deep water ocean circulation that is really driving a lot of the nutrient flux is being formed in the polar regions. And in particular, one example being in Antarctica, as we form sea ice, we melt out the fresh water and leave behind the salt, right? And salty water is dense. So as we increase the salt, we create really, really dense water, and that water sinks and drives ocean circulation. If we change sea ice extent, we change ocean circulation, and this has another feedback on the climate system and on the biological system and ecosystem of the ocean. So these changes in sea ice have potentially really, really large impacts on the global ocean, not just in the polar regions, all right? So climate itself is impacted by the response of the cryospheric system to the initial changes in climate. All right, one of the other reasons, and a big reason that we actually care about the cryosphere, is because of its impacts on society. And there are several, but the three I want to talk about today and the remainder of the time is sea level rise, water resources, and hazards. So sea level rise is the one that with the biggest global footprint, so we'll start with that one. And this is an image, again, this is sea level rise versus time, 1700s, and then projecting to 2100, okay? So we know sea level has been rising over this period of time, right? And these are different scenarios for, by 2100, what we might expect sea level rise to do. And they range anywhere from, well, at the absolute lowest end, about a 1/4 meter sea level rise to upwards of 1 meter sea level rise, 1/4 meter being extremely optimistic, 1 meter probably being on the other end of the spectrum, okay? If we look at the contributions to that and why sea level is and has been rising, this is actually mainly a projection, but it plays out true even in the past. This is net sea level rise in black. Most of it, about half of sea level rise, both in the past and in the future, is because the ocean's warming. You warm the ocean, water expands, sea level rises, right? The rest of it is due to ice. So if we melt glaciers from off the land, that water goes somewhere. Ultimately, it goes to the ocean, and it goes to increasing sea level. Counter to what most people think, most of that is actually mountain glaciers, not the ice sheets. Over short time scales, the mountain glaciers respond a whole lot faster, and they're contributing more to sea level rise than any of the other ice bodies, okay? Then you get into Greenland ice sheet because it both melts and calves in the ocean. It has the most dynamic response. And then the ice sheets. But notice something here. We have uncertainties on what the warming of the ocean would do to sea level rise. But even in the IPCC report, the last one and this one, we don't even quantify the uncertainties of glacier contributions or ice sheet contributions because it's that uncertain. We don't actually know to any degree of certainty how these will respond, which means that these values right here could be significantly higher or lower. This is a big uncertainty in our estimations of future climate change, and in particular on sea level rise, is the uncertainty in how the big ice sheets and the mountain glaciers will respond to a warming climate. So a lot of current research is going into this area right here, is just quantifying the response of glaciers to changes in climate. And in part, the reason so much effort's going into that is because the potential impact is huge and it's everywhere. So this is a 1 meter sea level rise, and the red is the land that is taken over by sea level, okay? And so if you zero in here on, say, the United States, much of the East Coast, the South, and even the West Coast, and a lot up in Alaska, big impacts, big changes in land area, but more important than the magnitude of the sea level rise is what we call the vulnerability to sea level rise. So it's not just the idea that water rises and floods the land, okay? It's, does that happen where we have ports, right? Because most of the world's economy, or at least a large percentage of it, is tied to our port systems, right? Is it happening in a region where we have saltwater encroachment into freshwater resources? That's a big hit to the system. Is sea level rising happening along a rocky coast or a sandy coast where erosion is going to be a major potential? Is it happening in a region where you're going to affect flooding due to storm surges or storms of any kind or hurricanes, right? So this is an example of that the USGS did. And this is for a 1/4 meter sea level rise. What regions will be impacted in significant ways and what regions won't, with the reds being very high. And you can see that it's not the same everywhere, even for the same rise in sea level, right? But notice anywhere we have a major port, potentially very, very vulnerable to even small changes in sea level. And then large regions where it's not going to be a huge impact, okay? But what we know is that on every single continent, you can plot up this map, and significant areas will be hit really hard by even a small rise in sea level. We know sea level will continue to rise. A big missing component in that is not knowing how the ice sheets and glaciers will respond, okay? And one of the big hopes being Antarctica being able to buffer that by increasing accumulation in Antarctica. But so far, we have been able to show that temperatures are increasing drastically in Antarctica in many of the regions, but very little evidence that it's actually increasing the accumulation in the interior. All right, so the other one is water resources and hazards. Many, many, many publications in top-tier journals, but also front-page news, especially in regions like Switzerland, where 50% of the energy is hydroelectric power, and that water resource in the summertime for that power is the melting of the glaciers there. And in fact, they've gone to extremes of actually trying to cover some of the glaciers with these tarps to reflect more solar radiation to try to save them. Most glaciologists consider this a sort of a Band-Aid on a gunshot wound, but it makes them feel better, so we'll just go with that. But it's a significant problem, and the area I want to look at as an example of that is actually a region in the Himalayas. So this is a little bit of a busy image, but we're looking at the high mountain region of Asia. So Himalayan down here, Tibetan Plateau, Tian Shan, Altai Mountains. Reds are borders of countries, dashed are disputed borders, right? I don't need to point out that this region is sometimes politically unstable, maybe more than sometimes. The purple are glaciers. Also notice that these borders all track within the glacier regions, right? And then the blue are the major rivers that feed more than 20% of the world's population. These glaciers through here have gained the nickname the water towers of Asia because they form the headwaters of all the major rivers, actually of most of the world, but in this region of a very politically unstable, large populations and many poor populations of the world. And some of the questions are, what impact will the retreating glaciers in this region have on the people downstream of this? So this is zooming into a little teeny country most of you, or many of you probably haven't heard of, the country of Bhutan. Okay, the Kingdom of Bhutan is squished between two powerhouses, China and India, and its average elevation is somewhere around, I don't know, 10, 11,000 feet above sea level, right? That's its average. The airport you fly into is at 11,000 feet above sea level. So this country is high. It's in the mountains, and they depend intimately on the mountain resources. This is an image in the northern region of Bhutan. So you can see many, many glaciers, glacial lakes, and rivers downstream of those. So Bhutan, just in this Lunana Valley right here, just downstream, is this beautiful Buddhist Dzong. Okay, this is the Punakha Dzong. It is one of the oldest Buddhist temples in the country. It's the political, religious, and cultural center of the country. In 1998, this glacial lake right here, formed by retreating glaciers, leaving behind a very weak, rocky, rubbly moraine dam, breached the dam and created severe damage to this temple. Now, this is one of the poorest countries in the world. They don't even own a helicopter. So getting in the resources, much less finding the resources into this region to fix this temple was a massive undertaking. And in fact, it was this undertaking right here where in 2000, and I'm not going to remember, 7-ish, Bhutan received the first money from the UN Climate Mitigation Fund for developing countries to do things to try to mitigate the impacts of climate change. And their goal was to try to artificially lower the level of this lake, because what happened is you lost this lake, but it reformed. And then this one formed uphill of it, and that one formed uphill of that. So you have 4 lakes nested, one above the other. If one goes, you've got a major catastrophe. Many people were killed in this flood, agriculture and livestock destroyed, and a major historical, cultural, and political religious source was also damaged. And in a new flood, this is likely to be just leveled and taken out. All right, so they had, and this country has maybe 600,000 people, maybe a little bit more, not many. Over 400 went up here to help with the lowering of that lake. That's a big percentage of the population. But because they don't have a helicopter, they can't get resources into there. It's about a 10-day trek to get to it. So everything had to be packed in. And then once they got there, because the mountains are the temples where the gods live, they can't blast. So this crew of 400 people would throw ropes around boulders and then heave them off the top to try to create an artificial breach. Didn't work very well, okay, in the end. But on top of that, just down valley of this, they installed their first hydroelectric power plant. This is the first national export they have ever had, and it's the form of hydroelectric power to India. This single dam increased their gross national product by more than 20%. Hydroelectric power in this region is a huge potential resource. But their question is it sustainable? 2 problems. As glaciers thin and retreat, the size and number of glacial lakes will increase. As glaciers retreat, the amount of water flowing through this river during the dry period will decrease. And in a country that's as poor as this, just the installation of that dam was an insane undertaking. Is it worth their time, energy, and resources to continue to put money into these dams, or is this something that's going to be a very limited, short period of time that's going to come back to actually be a problem in the end? So what a lot of my students and I are doing is actually trying to answer that question. And for sake of time, I won't go into the details. This is actually the work of Josh Maurer. There's just something kind of cool about this. What he's done is he's taken U.S. spy satellite imagery from the 1970s and 80s that was just declassified to go in and actually look at changes in these glaciers in this region over the last 30 to 40 years. There's just something poetic about using our spy satellites to do science. I don't know. Reds and yellows are decreases in glacier elevation, meaning losing ice. And you can see, for example, this region in 30 plus years, almost 100 meters, 300 feet or more, loss of ice at a single location across that area of these glaciers. Big changes over a fairly short period of time. Those are those 2 glaciers I showed you before, right here. You can actually see the trim line right there, the line where it was before, and you can see it having moved back. But this has happened in a very, very short period of time. This is then just showing, for a given change in temperature, what the change in glacier area in blue and meltwater flux as a result of that change would be in red. So just focusing on the minimum, it takes time for glaciers to respond, even if we had no additional warming, okay? for these glaciers just to come in a steady state with what's already happened, at least a 7% change in glaciarized area. So that's a 7% increase in area for forming new lakes and bigger lakes. And that results in a 30% decrease in meltwater resources. This gray background is the range and projections for future changes in temperature, with this just above 1 degree by 2100 being the absolute minimum to expect. We're talking about a 30% change in glacier area, a 70% decrease in meltwater flux. This is huge. In a meeting with the princess of Bhutan, when we were talking to her, she said, we were talking about this, and she said, you know, the hardest thing for them is the fact that they're not the problem. Their net carbon footprint is negative. And yet the impacts of climate change are going to be very, very real. And her point was this will challenge their very way of life. And this is not unique to Bhutan. It's the same story across this entire region. Glacier lakes, hydroelectric power, economy, freshwater resources, and potentially impacting large populations downstream. Okay? So in summary, if you get nothing else out of this, what I wanted to hit on was that Earth systems are tightly coupled, right? You hit one system, all the other systems will respond, okay? The cryosphere is just one of those systems, right? And what I've shown you is the cryosphere provides evidence that climate is changing. It provides a record of climate change that shows what's happening in the recent is unique in at least the past 1 million years, and that these changes will be amplified, right, by the feedbacks in the system, and it will impact society. Now, those impacts won't be negative everywhere, but all countries will be impacted, but some will be less resilient to those negative impacts. And in fact, these poorer countries are far less likely to be able to adapt to the changes that are happening in the system. Thank you for the time. I appreciate you all coming.